Welcome back to another exciting adventure in organic and biochemistry. So we're going to talk about alkanes in these videos. I think I'm going to try to break this one up into a couple of videos, so 2 or 3 videos hopefully, so it's not as long. But alkanes. Alkanes are hydrocarbons, right? They are a compound made completely of hydrogen and carbon, and that's it. So alkanes have all single bonds. Alkenes have one or more double bonds, and alkynes, right, we're looking just at the ending here, have one or more carbon-carbon triple bonds. We actually looked at that in our last video series. All right, and then we have arenes. Arenes are aromatic compounds. Now, our chapter 13 that we're going to look at is actually benzene-like rings. There are more aromatic compounds, especially if you use the Huckel rule of aromaticity, but we're going to look and focus on benzene only. So you're not going to have to memorize and have to figure out if something is an aromatic compound. I just want you to know that there are more aromatic compounds than just benzene, but we're going to focus mainly on benzene. Now this chapter, we're going to look at the alkanes. So let's start. These are the first 10 alkanes. They are all containing carbon-carbon single bonds only. This is the general formula for an alkane. You would want to know that. So knowing that allows me to say, you know, is C6H14, is that an alkane? Is C8H18 an alkane? Well, if N is 8, so C8H, what would the hydrogen number be for an alkane? It would be 2 times 8, which is 16 plus 2, so that would be 18. So that means we know there is no degree of unsaturation. There's no double bond or ring in this case. So we are going to be looking at that. These are the first 10 alkanes that we have. And you're going to probably want to memorize the names of these. Not probably want to, you should. So methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. So what am I really asking you to memorize is going to be the prefix. So 1 is meth, 2 is eth, so on and so forth. You need to know the prefixes. I'm going to have this in here a few more times, but you do need to know those. Now, 1 through 4 are mainly gases at room temperature, and they're fuel sources. So these are fuel sources. Most of our alkanes are fuel sources. But these are fuel sources, can't spell sources, for heating and cooking. So those are the ones that we're using to heat and cook, that kind of stuff. Most of us either use, liquid propane or natural gas, which is methane. Now, pentane through octane, so 5 through 8, they're actually very volatile compounds. Volatile, I can't spell today, or at all, I guess, lately. So volatile just means it's easy to evaporate. They're going to be easily moving to the gas stage, and they're also used as a fuel, but this is a fuel for combustion engines. Now, nonane down to hexadecane, which is 16, so C16 is hexadecane. They're actually very high viscosity fuels. That means they're thick, like syrup, and they're going to be used as the main component in diesel fuel or aviation fuel. So just some fun tidbits for you there. Line angle formulas are very, very important because it'll save us all a lot of time. This is a ball and stick model here. This is the line angle formula, and this is the condensed structural formula. And then you can also have the expanded formula where you draw it out like this. Now, if I have to draw every compound out like this, I am going to be here forever. So I'm going to start immediately using line formulas. Now, why is this beneficial to you as well? Well, here you have to remember every one of these hydrogens and to count every bond to carbon. You should always count your bonds to carbon anyway. But in the line angle formula, we actually allow you to take some liberties in the fact that we know that there is a CH3 here, a CH2 here, and a CH3. We're saying you already know all those hydrogens are there because you're going to make sure carbon has 4 bonds every time. So we're allowing you to not have to write them. But when you go to draw them, you're going to see as I do this, I'm going to say 2, 3, because this is carbon 1, this is carbon 2, and this is carbon 3. So when you go to write them and also double check, you're going to want to come up with however it works for you. 2, 3, 4. 1, 2, 3, 4. You could say 1, 2, 3, 4, 5. Every time there is an apex or the end of a line, it means there's a carbon there, unless we put another element there. So this is actually carbon 1, carbon 2, and this is not a carbon. There is no carbon here. This is an oxygen. So if you put another element there, it's no longer carbon. Okay, so these are line formulas. Every vertex and at the end of a line represents a carbon atom. Hydrogen atoms are not shown. It's much quicker. Constitutional isomers or structural isomers, these are also known as structural isomers. So they have the same molecular formula, but they're connected differently. So this is our line formula for butane, 1, 2, 3, 4. This molecule also has 4 carbons, 1, 2, 3, 4 carbons, but they're connected differently. So these are structural isomers. So I actually demonstrated this with, and I can show you real quick here as well. I don't know if you saw that, but my battery is running low, so I'm going to plug this in while we talk. But I demonstrated this with ethanol for you in the last video. So in the last video, I said, why do my Gen Chem students, they get kind of, like, why do we write it like this, Mrs. DeVos? And I say, well, it's not just to confuse you. It's because it tells me about the functional group and it tells me what I have. So that structural formula is important. But why do I need to know that that's an alcohol? Because what else can it be? Just plug this in real quick. Okay, there we go. So if I have CH3, CH2, and then I come down here, I have an OH. So this is CH3, CH2. I'm only going to do this right now because we're just learning these formulas. Or I could have CH3, O, CH3. So this is a CH3, and this is a CH3. This is ethanol. It's an alcohol. You're probably familiar with it. Not because it comes in the bottle, but because it kills all the viruses and bacteria, right? This is dimethyl ether. So this is an ether and this is an alcohol. They have very different properties, so the structural formula is going to be important. These are structural isomers of one another. They have the same molecular formula, but they are connected differently. So both exactly the same atoms, exactly the same ratios. However, the atoms are connected differently. So when they're connected differently, that means the constitution of the molecules is different. That's where the term constitutional isomers come from. Constitutional isomers are very common. You're going to see a lot of them in this class, so you're going to want to make sure that you can recognize them. So let's practice. I would like you to pause the video and try it. These are the two I'm talking about in A, and these are the two I'm talking about in B. And maybe you can see why I want to get away from these formulas, because they're kind of hard to read after a while. It's actually harder to read than a line formula, which looks nice and clean cut. So what I want you to do is pause the video and tell me, in each set of these two compounds, are they the same compound or are they constitutional isomers of one another? So in the first one, this is our main chain. There are 1, 2, 3, 4, 5, 6 carbons. Here, that would be our main chain, but then actually we can still go down here and over, and our main chain continues, it just turned. So these are the same compound. Single bonds are free to rotate. So what would this look like in a line formula? Again, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This is hexane. And this one, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It just turned funny, which it looks weird drawing it like this, but all of these bonds are completely free to rotate because there's nothing there to restrict their rotation. So this would also be hexane because there are 6 in a row. Naming them, I know you haven't learned that yet. Don't worry, we're going to learn it in just a few minutes. At the end of this chapter, we're going to learn how to name things, but naming them helps. So I'm actually going to name everything, even though I haven't taught you how to name yet, because I think it helps as we go. So I'm going to keep doing that. 1, 2, 3, 4, and I can come down here for 5. 1, 2, 3, 4, 5. I can't turn this one at all. Now, where are my substituents? My substituents are anything that comes off of the ring. 1 and 2, and here I have 1 and 2 substituents. So both of these are very similar. They both have a 5-carbon chain. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. But actually, so this one has methyl groups. These are called methyl groups at 2 and 4. And you'll learn this later. I'm going to actually erase these numbers because if I were to number this, I would actually have to number it this way. 1, 2, 3, 4, 5. We'll get there. Don't worry about that right now. So this one would be known as 2,4-dimethyl pentane. And this one will be known as 2,3-dimethyl pentane. There you go. So these are not the same compound. These are constitutional isomers of one another. They're both C7H16, but the atoms are connected differently in a different order. So I would like you to pause it and draw the 5 constitutional isomers with the molecular formula C6H14. So pause it. I'm going to go through the answer. Now, I am going to redraw these with line formulas in just a moment, but I want to show you how I work through these problems. So the first thing I can do is start with a 6-carbon chain. 1, 2, 3, 4, 5, 6. I can't move anything and I can't add anything. Now, a 5-carbon chain means I can take off one of those carbons and put it somewhere else. 1, 2, 3, 4, 5. But this can only go in certain places. It can't go here and it can't go here because if I put a carbon there, it's just going to extend the chain. So it can go here. 1, 2, 3, 4, 5. Or it could go here. 1, 2, 3, 4, 5. Or it can go here. But let's take a look at this real quick here. So if I were to number this one right here, I would say 1, 2, 3, 4, 5. And if I were to number this one, I would say 1, 2, 3, 4, 5. So both of those are at carbon number 2. So these are actually the same compound because we change how we number it to give the substituent the lowest number. So those two were exactly the same. So I'm erasing that one. And now we can have a 4-carbon chain. 1, 2, 3, 4. Now I have 2 carbons to place somewhere else. I can't put them there, but I can put one here and one here, or I can put both of them on the same carbon. So that's how I like to work through these, and then you would go back and you would have to add all the hydrogens. But instead of doing that, I'm going to erase this and I'm going to draw this with my line structures. So 2, 3, 4, 5, 6. This is hexane. 5 carbons. 2, 3, 4, 5. 2, 3, 4, 5. I can put it here, and that becomes 2-methyl, pentane. and this one would go here. 1, 2, 3, 4, 5. This would be 3-methyl pentane. 4 carbons. 2, 3, 4. I said I could put one here and one here. 2, 3, 4, or I could put them both on the same carbon. This one would be 2, 3 dimethyl butane. This one would be 2, 2 dimethyl butane. Sorry. So that's how you're going to want to do things like that. You're always going to want to name them if at all possible once you learn that, because then you'll know straight up that they're different compounds. As long as you name them right, of course, right? So let's get into naming. Oh, sorry. Let me erase that. You can see the book stuff. IUPAC stands for International Union of Pure and Applied Chemistry. All letters of complaint should be addressed to them, as I am just here to tell you the rules and show you how they work. I didn't come up with them on my own, I promise. I do understand that some of them are confusing, and some of them you might be kind of scratching your head and wondering why, but they probably had a huge conference about it, and there's a lot of smart people that went into making these rules. But let me tell you, focus on this naming, get this down, because this is going to be how we name everything from here on out. All we're really going to do is change the ending and change which functional group takes precedence. So there's about 8 alkyl groups. You're going to see 6 of them coming up. But then there's methyl. You're going to notice that the ending has changed for these than what you're used to, because it was methane. There's ethyl. And then there's, once we get to 3 carbons, there's going to be something that changes. I'm going to talk about this in just a minute. I just want to put them all down here for you in a minute, for a moment, so that you know them. Propyl, isopropyl, butyl or normal butyl, sec-butyl, tert-butyl, and which one didn't I write yet? Oh, isobutyl. All right, so these are historical names that are accepted by the IUPAC, and they're integrated into our modern nomenclature so that we don't have to come up with a secondary numbering system is most of the time why it's that. They're called alkyl groups. Alkyl, remember, in the last video, I called them R groups. So an alkyl group is abbreviated as an R group, or we can actually remove a hydrogen and put a functional group that we learned about in the last video. So they could be an alkyl group or a functional group. So I put this is not in your slides. I just re-put this here because this is really important. You're going to want to refer to this slide, make flashcards, whatever you have to do to know these 10 names, know the general formula, and that the ending -ane means single bonds. Let's get into the alkyl groups. What is an alkyl group? It's an alkane where we removed one of the hydrogens, so we changed the ending to YL. So its name, we replace the ane and add YL. So methane actually becomes methyl. This is our hydrogen we're removing here. It's gone. And instead of being CH4, we're now CH3. So we remove a hydrogen. That means there's a spot on this carbon for something else to bond here. So we can bond, and that's where it can be an R group, or it could be a functional group. We can put something else on that group. So why are there different ones once we start to get to 3 carbons? Well, if I go back one slide, no matter which of these hydrogens I remove, if I remove this one, or this one, or this one, or this one, it's all going to be the same. It's going to end up being CH3. And they're all free to rotate. We don't notice any difference So these are what are called equivalent hydrogens. Oh, I'm still in the equivalent. Meaning they're all the same. No matter which one I remove, it's going to give me the same result. Well, so this is methyl. Let's look at ethyl. So if I look at ethyl and I look at, why is it changing the color? Okay, if I look at ethyl here, I have a hydrogen. I have a hydrogen here, and I have a hydrogen here, and here, and here, and here. All right, so I have 6 different hydrogens to choose from. Well, let's just say, let's pretend I doesn't want to do that. Okay, let's try this way. Aha, 2 can play this game. Let's say I remove that hydrogen and I put a chlorine on there. That would be carbon 1 and carbon 2. That would be 1-chloroethane. Okay. I'm going to erase this because you guys can go back anytime. What if I were to instead, this does not like doing my, instead put it here. That would then be 1-chloroethane. And that would be the same if I put it here or here or here or here. So all of these hydrogens are equivalent hydrogens. So no matter where I take the hydrogen from, I'm going to get the same result. So I don't have any difference. So I just have ethyl. Starting with 3 carbons, we're going to have some differences in where we remove the hydrogen from and what happens. So let's bring up these terms again. Primary, secondary, tertiary. If you remember talking about those in the previous video, we talked about them a little bit different for oxygens, for alcohols. Was it a primary alcohol, secondary alcohol, or a tertiary alcohol? Or we also talked about it with amines, but we didn't really talk about it with carbons. So carbons can also be primary, secondary, and tertiary. This is a primary carbon, hydrogen, hydrogen, hydrogen. It's bonded to one other carbon. So this is a primary carbon. You look at the carbon of interest. If this is our carbon of, I've really got to stop doing that. It's kind of annoying, huh? All right, I meant to do this and this. So if this is our carbon of interest, we look at how many carbons is it attached to, other than it, the one, you don't count itself or anything like that. So that's a primary. A secondary carbon looks something like this, has 2 hydrogens and 2 carbon groups. Now there could be more carbons out here, but we look at the one we're interested in, and that one is attached to 2, so it's, I'll get there. So it's secondary. These ones don't count. Then for this one, we have 1, 2, 3. This would be, we're looking at the carbon of interest is this carbon right here. So how many other carbons is it attached to? 3. So it's tertiary. Now we can have a quaternary carbon. Quaternary carbons are possible. So you can have a carbon bonded to 4 other carbon groups, and that's a quaternary carbon, but it's not an alkyl group in that case. So that's why we don't count it in this slide. But you can have quaternary carbons. So the degree of substitution of the carbon of interest, you're going to count how many other carbons that carbon's attached to, and that determines whether it's primary, secondary, or tertiary. Common names, that old system we're referring to with the ISO-SEC chart that I was talking about, we're going to look and see why that is. But this slide is telling us about, first up, what the ISO group is. This is an ISO group. Okay, well, an ISO group is always kind of like a Y. So in a line structure, well, that doesn't really work unless I do that. This would be an ISO group. It looks like a Y. Well, let's see what it is. It would be, did it again, CH3, oh, excuse me. I'm having a hard time with this today. All right, so that would be CH is what I meant to write there. CH, CH3, CH3. It was bothering me because I meant to write it in red, but whatever. So CH, CH3, CH3, that's what this says. CH, CH3, CH3. You can see it written out here. CH, CH3, CH3, also here. So in the old naming system, way back when, they used to name compounds just by how many carbons were there in total. So if there's 1, 2, 3, 4 carbons, it's butane. Well, this one also has 4 carbons total, 1, 2, 3 in the longest chain, but it has this fourth one, so it's also going to be a butane. And they said since it has this group, it's isobutane. This has 1, 2, 3, 4, 5 carbons, so it's pentane. This one also has 1, 2, 3, 4 carbons in the longest chain, but it has this fifth carbon, and since it has this Y group in there, that iso group, it becomes isopentane. So be thankful for this IUPAC system. Even though it's a lot to memorize, it's systematic. Once you get it, you're just going to get it. You're going to understand that it does have a system, and we don't have as much to memorize. So iso is something that has, you know, these 3 carbons in this order, and it shows that branch, that specific branch. So when we come to propane, now using the IUPAC system, coming to propane, we have different hydrogens. So if this is CH3 here, right, and this is CH3, no matter which of those hydrogens I take, I'm going to end up with this result. So if I take one from one of the terminal or the end carbons, I'm going to get this result here. And that's known as propyl or normal propyl, N-propyl. Most of us just write propyl these days, but it doesn't matter. But if I take one of the hydrogens from the CH2, I'm going to get this. Now this should look familiar to you from about 3 seconds ago when I said we have CH, CH3, CH3, or this group. That is what? Iso. So that's isopropyl. It's going to take some practice to remember these ones, but once you get these 6 different groups down, I remember I said there's 8, but methyl and ethyl, I'm not sure they really count that much as being that hard to understand. But these are not all equivalent hydrogens. So if I were to say how many different sets of equivalent hydrogens are in this group, these would be one set and these would be a second set. So there are 2 sets of equivalent hydrogens. I do not know what's going on with my spelling, and of course it's going to be on video for everybody to see, but whatever. All right, now starting with butyl. So if I look at butyl, I have 2 CH2s in the middle that no matter which one of those I take a hydrogen from, I'm going to get this result. If I take one from one of the terminal CH3 groups, because they're equivalent, I will get this result. So again, I have 2 sets of equivalent hydrogens, and if I take from either one, I'm going to get a different result. This one and this one form, obviously I'm hoping you can follow the highlighter, this group here, which would be normal butyl. Let's look at this carbon here. How many carbons is that one attached to? 1. So it is a primary or normal butyl. If I look at this carbon here, how many other carbons is it attached to? 1, 2. So it is a secondary carbon or sec-butyl. So that's where that name comes from. It's a sec-butyl. Notice that this is hyphenated. That's our first hyphenated thing. I'll talk about why that's important in a little while. But remember what we looked at a few slides ago, butyl doesn't have to come, or butane, anything that had that 4 carbons back in the day was named butane, but they didn't all have to be in a line. So if we start with isobutane, like this, I'm just highlighting the whole compound for right now, we have a different situation that can arise. So if I take a hydrogen from here, or here, or here, those are all equivalent hydrogens, and it will give me this result. But if I take a hydrogen from here, I'm going to get this result. So this one, if I count here, or I'm sorry, I don't even need to count. Let's look at this. 1 CH, a CH3, and a CH3. Does that look familiar yet? You see that Y kind of look to it? That is iso. So that's our isobutyl. Also, this carbon is attached to one other carbon, so it's primary. This carbon is attached to 1, 2, 3 other carbons, so it's tertiary or tert butyl or T-butyl. T-butyl or tert butyl, both are fine. They're usually italicized a lot of times. So excuse me, this one is also hyphenated, so that's going to be important. We know the basics of these alkyl groups now. We can actually get into some of the naming rules. Again, just to remind you, the IUPAC system, you're going to need to know for sure 1 through 10. It doesn't hurt to know more than that, but I'm not going to ask you more than that on the test. I'll just keep it 1 through 10, or I'll give it to you or tell you what it is. I'm not going to ask you to name it if it's more than 10. So you need to know 1 through 10. So the prefix are these prefixes down here, 1 through 10. The suffix depends on what we're having as our functional group in the end, but for right now, with the basics, all we have are carbon-carbon single bonds or carbon-hydrogen single bonds, so it's going to be ane. First up, the first thing I'm going to have to do is find the parent chain. So find the longest chain in the compound. So that's going to be the base or the parent name. Now, this can be quite easy and it can be difficult. Remember, it can bend, it can twist. And if it bends and it twists, it might be harder to find, but you can do it. So I'm going to show you like a little harder example where we have multiple possibilities for this different structure here. So let's try this. 2, 3, 4, 5, 6, 7, 8, 9. All right, 1. So I'm going to draw this 3 times. 2, 3, 4, 5, 6, 7. It's not like saying something 3 times fast. And we got to try to find the longest chain. So that is something to start with, right? Start to find the longest chain. I'm going to do the longest chain. I'll just do it in yellow. That'll be fine. All right, so here we could go simply 2, 3, 4, 5, 6, 7, 8, 9. But we could also do 2, 3, 4, 5, 6, 7, 8, 9. Or we could say 2, 3, 4, 5, 6, 7, 8, 9. Anything that's not directly part of the base chain or the parent chain is going to be called a substituent. So a substituent. How many substituents do each of these have? 1, 2. This one has 1, 2, 3. And this one has, I'm sorry, 1, 2. When you have something like this, where you have a situation where you have multiple chains of equal length. So we don't know which one should be the parent chain at this point. You want to choose the one with more substituents. So not this one, not this one, but this one. If we were to choose one of these, we would have to almost do a second numbering system, or we would have to use that old numbering system with the 1, 2, 3, 4. This would be isobutyl. So this would be, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. This would be 3-methyl, actually, yeah, no, we would have to, that's what I get for making stuff up in my head, right? Okay, so we would have to do 4-isobutyl, 3-methyl nonane. But with the second one right here, oh, I erased that parent chain. With this one, we can say I have a substituent here, here, and here. If I number from this way, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. If I were to number from a different direction, I would have 1, 2, 3. And here I would have, and that's the only way I can number it. So my first substituent would be a 3 in this way, and my first substituent would be a 2 from this way. And we always want our first substituent to have the lowest number possible. If we have a tie, we'll talk about that later. All right, so what would I name this one? How would I name this one? And again, we're getting there. I haven't given you the rules yet. I'm just doing this so you have practice later. I have 2 methyl groups. These are both methyl and methyl. All right. So, and I have a 1, 2, 3, 4. I have a butyl. Notice I don't need any second numbering systems. I don't need to use any of the old naming system. I can just say 2, oh, nope. So why did I write those there and then not look at them? That was silly. Sometimes when I'm doing this, or most, I don't know, most of the time, sometimes I write out the names of the substituents so I can look at them because we write them in alphabetical order. I was just trying to do this quick, but 4-butyl, that's supposed to be a dash. It's important. So dash 2, comma 7 dash dimethyl nonane. Okay, so that's how that one would be named. That is the correct name, so I'll leave that one there. But when we run into this situation where you have more than one parent chain, the rule is to choose the one with the more substituents. That's the point. All right, well, what if we have a ring? So we're going to start talking about rings at the end of this chapter. Let's say I have a 5-membered ring here or a 5-membered ring here. How do I know if the ring is part of the parent chain or not? So let's look at the parent chain. Here, the parent chain would be the ring, because the ring has 5 carbons and the chain only has 4. But here the parent chain would be the straight chain and not the ring, because the ring only has 5 carbons and I chose the highlighter again. So this one has 1, 2, 3, 4, whereas the ring has 5 carbons. The ring here has 5 carbons, but this has 1, 2, 3, 4, 5, 6. So I would choose the ring to be a substituent. So ring is a substituent here. And here the ring is the parent chain. We'll talk about rings towards the end of this. I'm not going to go into naming those right now. All right, so what we're going to do right now is practice finding the longest chain. So I want you to pause this. I want you to find the longest chain that you can find and then try to just name that longest chain. Since you paused it, I'm just going to keep going. The longest chain here would go this way, and then it would turn down here. And in B, it would go this way. Let's see. It's hard at first, but then it, just like everything else, it becomes easier as you learn it. And that way I have, let's see how many substituents. I have 1 substituent here, and I have 2 substituents here. This one would be 1, 2, 3, 4, 5, 6, 7. So this would be heptane is our parent chain. And this one, 1, 2, 3, or 1, 2, 3, 4, I would number from this way. 1, 2, 3, 4, 5, 6, 7, 8. So it would be octane. Once you learn how to find the parent chain and you can successfully find the parent chain, we need to learn how to deal with substituents. So there's our longest chains. And let's go to how to do and how to deal with substituents. So what do we do with substituents? Well, first let's find the longest chain. All right, well, for this one, this is our longest chain here. Pretty easy on this one. This one you could do, up if you wanted to. You can go straight across. I'm probably pretty straight-laced. In this way, I'd probably just go straight across. Just how I do it. Then we have to number them. So how do we number them? Once you get the parent chain, identify where the substituents are, and then you want to give the substituent the lowest value. So in this one, I could number it 1, 2, 3, 4, 5, 6, 7, or I could number it 1, 2, 3, 4, 5, 6, 7. If I do the first way, I end up with this having a 3. If I do it the second way, it has a 5. So which do you think is correct? Ooh, whoops. So that way is correct. I can put the highlighting back in there if you want me to. And we would go this way because when our substituent has a 3 and not a 5. Our next one really can go either way, but you could say 1, 2, 3, or you could actually say 1, 2, 3. It doesn't matter either way. The substituent has a 2, so that one doesn't really matter. Sometimes that happens. If you have a tie, then you look at the next one. So always want the lowest set of numbers possible. So we're going to use a number to connect a number and then a hyphen. So this, I did not mean to erase that. I meant to circle it. We're going to look at these. We're going to use a number. So this is number 3, 3 hyphen. It's a methyl group, so we write methyl. And then hep for 7 heptane single bonds. This means 7. This means single bonds. And this means it's a CH3 group. So everything has a meaning. In this one, 1, 2, 3, this would be 2 methyl propane. The old name for that would have been isopropane. Remember, it's different than isopropyl because it doesn't have a missing hydrogen. Okay, these are full saturated compounds. I want you to practice, so pause and practice. I'm going to keep going. So pause and practice, find the longest chain, and name it. There's the longest chain for that one, and here's the longest chain for this one. We have 2 substituents. On this one, we have a methyl and an ethyl. Here we have a methyl. If we have more than one substituent, so this is a methyl, and this is an ethyl, we're going to put them in ABC order, alphabetical order. But we do still have to number them. So 1 through 8, it's an octane. So we say octane. Then we look at the substituents. We have ethyl, which is going to come first, and methyl, which will come next. So 5-ethyl, 3-methyl octane. Notice there's no space here. That's on purpose. This compound we would number 1, 2, 3, 4, 5. 2-methylpentane. So if you have a substituent that occurs more than once, you're going to use the prefix di for 2, tri for 3, tetra for 4, penta for 5, hexa, just to keep going, for 6, hepta for 7, octa for 8, nona for 9. I think you get it. So those we're going to use, but it's important, these are not used for naming. So even though it tells us how many there are, we do not use these for alphabetical order. So if it's dimethyl, we'll use the M from methyl, not the D from di. So when we have 2 or more, if we have a branch that occurs more than once, we're going to number the parent chain again, giving the lowest numbers. So 1 through 6. We have 2 methyl substituents. So 2,4 dimethyl hexane, not 3,5. So when we have 2 or more different substituents, we're going to put them in ABC order. We're going to number the chain. Again, we're following all the same rules. That gives the lowest substituent. So first we got to find the parent chain. Where's our parent chain? In this one, it's going to be this one. Actually, this is the same one that we had originally. I just didn't name it the whole way for you yet. This is our ethyl, and this is our methyl substituent. So we have a methyl and an ethyl, 2 different substituents. We have 1, 2, 3, 4, 5, 6, 7. So it's heptane. What's going to come first? So heptane is our final, but what comes first, methyl or ethyl? Ethyl is going to come first. So should I number it 1, 2, 3 from this way? Or this brings up a good point, 1, 2, 3, 4, 5, 6, 7. Both directions, we end up with 3 and 5 for our substituents. If the substituents are equal distance from both ends of the chain, and it doesn't matter which way you go, it still matters, you do that alphabetically. So actually we're going to number this way on the bottom because alphabetically ethyl should come first because it's an E and not an M. And I'm pretty sure you guys all know your alphabet, but you know, if you need to, practice. So we end up with 3-ethyl, 5-methyl, and this is heptane. Yeah. Okay. Practice this one. Find the longest chain. So pause it, find the longest chain, and name it. If I start numbering from this side, I get a lowest substituent number of 3, but if I start from this side, I have a lower substituent number of 2. So I'm going to say 1, 2, 3, 4, 5, 6. So we end up with a hexane, and we have a methyl and an ethyl. Ethyl should come first, then methyl, and then you put the numbers in with a dash. 4-ethyl, 2-methyl, hexane. Now, this is where we come into, why did she tell me those were hyphenated? Because this is where you might think that the IUPAC is a little bit hard in some cases. But first, let's find the longest chain. Now, if this, I just want to say, if this were written in a line structure, it would look a lot easier. But let's highlight the longest chain first. So our longest chain is here. And then we have our substituents. So we have this group here and this group here. What would this look like in a line structure? Let's draw a line structure. 1, 2, 3, 4, 5, 6, 7, 8, 9. 2, 3, 4, 5, 6, 7, 8, 9. Something like that. I drew it a little funky, but it's just a lot cleaner and a lot easier to read. So this is why it's easier to do line structures, that they're actually a lot easier to read, a lot easier to look at. So I just thought I'd show you that. All right, we have 4 total carbons in this group. And if I look at this carbon, before it was attached here, so we don't count this one right now, how many other carbons is it attached to? So it is sec-butyl, right? So sec-butyl. And this one makes our Y, CH, CH3, CH3. This is isopropyl. The rule is that hyphenated prefixes and number prefixes are not considered when alphabetizing. So the first letter we're going to look at here is the B for butyl, but this one we are going to look at the I for isopropyl. I didn't make the rule. Keep that in mind. I did not do that to you, but I'm teaching it to you. So first of all, we have how many carbons? 1, 2, 3, 4, 5, 6, 7, 8, 9 for nonane. We have sec-butyl. We have isopropyl. And we have the numbering. So I numbered to give them the lowest values. Isopropyl coming in at carbon number 4 and sec-butyl coming in at carbon number 5. But I think the whole point, well, not I think, I made this slide. So the whole point of this slide was to show you that we do not use the S from sec, but we do use the I from isopropyl. I want you to practice it. So pause it and practice it, please. Find the longest carbon chain and name it. So what we're going to have is one ethyl and we have dimethyl, and the di does not count. So we're going to be looking at the M from methyl. So first off, it's 7 carbons. So we're looking at 1, 2, 3, 4, 5, 6, 7 for heptane. Heptane, then we have the ethyl. We look at the E for ethyl. And dimethyl, we look at the M for methyl. Then we put the numbers in. So for ethyl, we have 5. And for dimethyl, we're going to have 2, 3 hyphen. We always have hyphens between numbers and letters and commas between numbers. Again, I want you to try it. So find the longest carbon chain and name it. Pause it. Don't forget to pause it. So with this one, we have decane. It's actually 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons for decane. Then we are going to put down the isobutyl, the I, right? The I from isobutyl. Ethyl, E, comes before that. So the ethyl group here has E. Dimethyl, we have 2 methyl groups again. The M is what we're going to use for that. So that comes up next. And we just put the numbers in. For ethyl, we're at carbon number 6. Isobutyl is at carbon number 6 as well. And then we have 3, 3. So even though we have 2 at the same number, they don't have to be at the same number, so we do have to put that same number in there twice. So even though you're writing it twice, you do have to write it twice. All right, that's it for naming straight chain alkanes. We're going to look at cycloalkanes, but I think I'm going to do that in the next video.